So first of all, this time instead of using Python as the interpreting language, I'm going to use Sage. Sage is enhanced beyond Python a bit with some algebraic functions and plotting utilities that are very useful in mathematics. There are a couple of syntax differences, but by and large you can use Python as you normally would. The main thing that often confuses people is whereas in Python you would say 2 cubed this way with star star, Sage understands the caret symbol 2 caret 3. Okay, so let's do a quick example of how to plot. One thing you often want to do is have a collection of data and do a scatter plot. A nice way that Sage can plot this is interpreting as a list of points. So let me make a list of points, a point being a pair, say 1, 2, and 2, 4, and 3, 9. I can say point L. So the command point takes a list of tuples, whether pairs or triples, and puts it on a scatter plot. Let's make this a little more interesting. I'll make a list, that list, and I'll make another list which is, let's auto-generate it as, let's say x and x squared times 1.5 for x in range, let's say 10. Now suppose I want to plot both of these together. Well, point L1 is simply the plot of the first list. If I do point L2, notice what happens is it only shows me one plot. That's because, of course, in Sage Math Cell, it only outputs the last thing that you ask for. However, each of these plots is actually an object in the object-oriented language. So we can give each of them a name, say P1 and P2. And one of the really convenient things about Sage is they've interpreted the plus sign as overlaying graphs as if they are transparencies. So I can say show P1 plus P2, and now we have both plots overlaid. You can see there's the points from L1, here are the points from L2. Now in a graph like this, you might want to disambiguate the two different pictures, and we can do that with attributes in the different plots. So the point command, I can say things like color equals magenta and color equals green. So now we see you have the magenta and green points from each plot. We can also do things like, let's say size equals 10. I think that's the default. Let's try size equals 20. So now you can see the green points are twice as big as the magenta points. Sometimes if I just want to see a picture, I do this. I make the sizes quite large, so it's easy to figure out what's going on. Now this sort of plot also works in 3 dimensions. So let me extend these to be, say, 1, 2, 0, 2, 4, 0, 3, 9, 0. And let's say take this to be this shape. And although it looks a little strange right now, we get a 3-dimensional plot of the magenta and green. And if your browser is a modern browser, you can rotate it, you can zoom in, and so on. Of course, it looks a little silly with the big balls because I have this size equals 50 command. If I remove that, it'll look a little bit more reasonable. So point does scatter plots in 2 or 3 dimensions, and you simply feed it a list of points. Okay, next, let me also point out that we can use Numpy, right? That's our favorite numerical array package. And if I say import Numpy, just like I would in pure Python, remember we're using the Sage interpreter this time, but I can import Numpy and say A is numpy.array. In fact, let me do this. I'll say numpy is A range, let's say 12. And I'll do show A. So show is a command that's not in pure Python, but is in Sage, that lets you basically display any object that you're looking at in some nice way. So there's an array from 0 through 11. And to make it into a list of points, let me just do this. Let's say a.shape equals, let's make it 6 by 2. Okay, so now I have a 6 rows and 2 columns array. That was just simply a way to demonstrate how to build an array quickly for an example. So now what I can do is, remember that if you loop over an array, you actually loop over the rows. So if I say for p in A, show p, each iteration of that loop is actually giving me a row of this. And each of these is in turn interpreted as a pair or a list of 2 objects. So that means I can feed an array straight to the point command. So I can say show point A to scatter plot those points. So here we go, 0, 1, 2, 3, 4, 5, and so on, just as displayed here. So if you have an n by 2 array or an n by 3 array and you want to plot it, where the columns represent the x1, x2, x3 coordinates and so on, and each row is a different data point, you can simply say point, show point to display it. And of course you can also alter it, say color equals orange. And there's our orange points. Now sometimes you don't just want to scatter plot, you want to connect the pictures. So let me make a few alterations here. I'll call this P1 for my orange points. Maybe I'll make them a little bit bigger. Let's say size equals 30. I can also use a command called line, which connects the points with lines. So line is just like point, but instead of simply scatter plotting the points, it connects them with lines. Okay, so we can scatter plot or connect the dots on any array of points. Let me do another example here. Let me use the random command. So numpy random rand n. I won't show the array. What I will do is show the points. What we have here is a normally distributed collection of 100 points in R2. So this is a very useful command if you want to generate data sets, is to use numpy random rand n, make an array, and then if you want to visualize this data set, you can do so. Now because of the broadcasting rules you've read about with numpy arrays, we can do things like take this array and multiply it by, say, 10, 3, and add 5, 5 to it. Let me do this a little more carefully. These all have to be arrays of the same shape. And if you think about the broadcasting rules, what this is going to do is take the normal distribution, stretch it in the x direction by a factor of 10, therefore changing the standard deviation in that direction, and the y direction by 3, and then shifting the center to 5, 5. And indeed, that's exactly what we see. So here we have a normal distribution with mean at 5, 5, and it's got a square root of the variance in the x direction of approximately 10 and the y direction of approximately 3. So we have some sort of ellipsoid here. So this is a very useful way to generate sample data if you want to try things. For example, one way of interpreting the singular value decomposition is to take a data set like this and ask which of the directions and which the variances along the major and minor axes. So we'll be discussing that when we discuss the singular value decomposition next week. Finally, I'd like to show some other plotting commands that are often quite useful. Again, these are Sage plotting commands, not pure Python plotting commands, but that's okay for our purposes. So let's suppose you want to define a function. Let's say you want to plot a parabola. The command is simply plot. And you can give it a variable name. In fact, this is a Sage detail. If you're going to use a mathematical variable, not a programming variable, you say var, and in quotes give the name of the variable. So I'm going to use the variable x as my plotting variable, and then a domain over which to plot. So if I say, let's call this P1, and I want to show it, we get our nice plot. Oh, I'm sorry. Ha. I plotted 2 functions there, not 1. So you can actually give plot a list of functions. So for example, maybe I want to plot x squared, and I want to plot x cubed, and I want to plot x to the 4th, let's say sine x, all in the same plot. I can give it a list of functions. So there's 3 different things plotted. This, by the way, if you happen to be teaching calculus, this is an extremely useful command, say for comparing sines and cosines on the board. It's very easy to type live when you're in front of a lecture. So we can do that, and then we can also do things like this, right? So any plot, let's say point of t comma t squared for t in range 10. So here you can see I'm making a list of points. I'm going to apply the point command to that list. I'm going to color them orange and make their size 30. And I can now do P1 plus P2. And there's my points. So you can make any combination of pictures, and by adding them and running show on the sum, you get sort of a transparency overlay of the different pictures.